At night, the universe looks calm. Stars, silence, a sky that feels like it's been doing the same quiet thing forever. But that silence is the weird part. Because when you zoom out and do the simplest math, how many stars there are, how old the galaxy is, how many chances life has had, you start expecting noise. Not literal sound, obviously. Signals, artifacts, megastructures, weird chemistry, something that screams someone else is doing physics over there. And instead, we get basically nothing. It's like walking into a city the size of a continent, turning on every radio station, checking every street and finding the lights off. No traffic, no conversations, no billboards, no leftover pizza boxes, just wind. That's the Fermi Paradox in its simplest form. The universe looks like it should be busy, but it looks empty. And here's what makes it such a powerful question. It doesn't ask, are aliens real? Like it's a trivia contest. It asks something sharper. If intelligent life is common, why don't we see any evidence of it? This story is not going to be a monster movie where the answer is always because they're hiding behind the moon. It's going to be more interesting and more scientific than that. We're going to build the paradox carefully, using what we know about stars, planets, time, and physics. Then we'll walk through the leading families of explanations. Some comforting, some unsettling, and some that sound scary, mainly because they force us to think like grown-ups about risk and scale. We'll ask questions like, what if we've barely searched, and the universe is full of whispers we're not listening for? What if space and light speed delays make civilizations invisible most of the time? What if the big barrier isn't finding aliens, but surviving long enough to become noticeable? What if expansion of the universe itself fences everyone into lonely islands? And what if the silence is not an accident, but a strategy? By the end, you'll have a map, not a final answer. Science rarely hands out those on day one, but a clear map of what the silence could mean and what kinds of evidence would move the needle. For now, hold on to one image. A dark ocean at night. You're on a small boat. You see no other lights. You hear nothing. You could conclude you're alone, or you could conclude something else. Maybe everyone learned a long time ago that turning on a bright light out here is not always a good idea. Hello, and welcome to Sleepy Space Traveler. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. All right, let's start with the foundation. What the paradox actually is, what assumptions create it, and why the galaxy is big isn't the same thing as aliens should be obvious. To understand the Fermi Paradox, we have to do a little mental housekeeping first, because the paradox is not aliens exist, but we haven't met them. That's just a statement of disappointment. The paradox is a tension between two ideas that both feel reasonable. 1. The Milky Way is huge and old, with an absurd number of stars and planets. 2. We don't see any clear signs of galaxy-spanning civilizations. Put those together, and you get to the classic line attributed to Enrico Fermi. Where is everybody? That's a paradox. Not a proof, not a prophecy. A mismatch between expectation and observation. So let's build the expectation carefully, because this is where the whole debate lives. Start with the age problem. The Milky Way is billions of years old. The Sun is about 4.6 billion years old, which already tells you the galaxy was forming stars long before Earth existed. That means there have been enormous stretches of time for planets to form, cool, develop chemistry, evolve life, and, if the dice roll that way, produce technological civilizations. Time is the real fuel here, not rocket fuel. Evolution fuel. Now add the numbers problem. Even if you avoid quoting exact star counts, the qualitative point is unavoidable. The galaxy contains a mind-bending number of stars, and modern astronomy has confirmed that planets are common. So the raw trial count is huge. Lots of stars, lots of planets, lots of time. This is what makes people feel that intelligent life should have happened many times. Now the next step is the colonization intuition. If a technological civilization becomes spacefaring and decides to expand, even slowly, it could in principle spread across large parts of the galaxy over long timescales. The paradox feels strongest when you imagine not a single spaceship, but a long-term process. Exploration, settlement, industry, replication, and expansion. And here's the key piece people often miss. You don't need faster-than-light travel for this intuition to work. You only need speeds that are slow by sci-fi standards, but fast by human standards, and enough time. A useful analogy is mold on bread. Mold doesn't teleport across the loaf. It spreads locally. It colonizes nearby territory. Then, from those new spots, it colonizes more territory. Given enough time, the whole loaf changes. That's the expansion wave intuition in a nutshell. You don't need one ship that crosses the galaxy. You need a process that keeps making new starting points. This is where the script you uploaded leans on the idea that if grabby, expanding civilizations exist, they could dominate the future. So the simple expectation becomes, if civilizations like that are common, some should have had enough time to leave obvious signatures. And that brings us to the observation side of the paradox. What do we actually observe? We observe that the sky is not obviously full of alien engineering. We don't see undeniable megastructures changing the light of stars in unmistakable ways. We don't see galaxy-wide communications blaring across every frequency. We don't see probes parked in obvious places with "hello" painted on them. And SETI, the search for extraterrestrial intelligence, has not yet detected a confirmed artificial signal. So the paradox is a contrast. High expectation from many stars, plus much time plus expansion is possible, versus low evidence from no clear signals or artifacts. Now here's where it gets interesting, because the paradox is not one question. It's a bundle of hidden assumptions. If you remove certain assumptions, the paradox weakens. If you strengthen them, the paradox becomes sharper. So let's list the key assumptions that create the "they should be obvious" feeling. Assumption A. Life is not extremely rare. If the origin of life is incredibly unlikely, so unlikely that it happens once per galaxy or less, then the paradox mostly evaporates. The sky would be quiet because there's almost nobody in it. Assumption B. Intelligent life is not extremely rare. Even if microbes are common, maybe the step from microbes to complex multicellular life is rare. or the step from complex life to tool-using, civilization-building intelligence is rare. If so, again, fewer civilizations. Assumption C. Technological civilizations last long enough to be visible. This is the lifetime assumption. If civilizations tend to self-destruct quickly, or stagnate, or retreat into low-energy modes, then the window where they're loud may be short. The galaxy could have had many civilizations, but each one flickered briefly and vanished. This connects directly to the great filter family of ideas, including the scary possibility that the filter could be ahead of us. Assumption D. Civilizations expand in an obvious way. It's possible that the smartest strategy is not expansion, but optimization, staying compact, efficient, and hard to notice. Or they expand with minimal waste heat and minimal electromagnetic leakage. Or they build in ways that don't look like big, shiny structures. Assumption E. We would recognize their evidence. This is the interpretation assumption. The universe might contain signatures we haven't learned to interpret as artificial, or we're searching the wrong channels. Assumption F. The galaxy is easy to traverse and settle. Even if interstellar travel is physically possible, it might be economically insane, socially unattractive, or risky in ways that prevent widespread colonization. Assumption G. We are not early. This is a subtle one. If we are among the earliest technological civilizations, the sky could still be quiet because the galactic era of intelligence is just beginning. Civilizations could be rare at this moment in cosmic time, even if they become common later. Now, when people say scientists solved the Fermi Paradox, what they usually mean is they found a framework that makes the silence feel less surprising. The script you uploaded leans hard into frameworks like grabby civilizations, strategic silence, dark forest, and various cosmic or technological filters. But before we go into solutions, we need one more critical idea, because it's the most common mistake in Fermi Paradox conversations. People confuse big with well-searched. The galaxy is big, yes, but our search effort has been tiny relative to the space of possibilities. It's like taking one sip from the ocean and saying, no fish. So the next step is to get realistic about the search itself, what we've actually looked for, what we haven't, and why we haven't found anyone, is weak evidence unless you specify we've looked for this kind of signal, in this range, for this long. If the Fermi Paradox is the feeling that they should be obvious, then this part is where we gently take that feeling by the shoulders and say, okay, but have we actually looked? Because the biggest hidden trap in this whole topic is assuming that the sky is quiet means nothing is happening. In reality, we've searched a tiny fraction of the ways intelligence could show itself. It's like walking into a gigantic library the size of a planet, opening one book to page 3, and concluding no one wrote anything. So, let's get clear about what searching for aliens has mostly meant so far, and why a perfectly busy galaxy could still look empty from our current viewpoint. The first search type, radio listening, classic SETI. Historically, the most famous approach is to listen for artificial radio signals. Why radio? Because radio waves travel well through space. They can cross interstellar distances. And we know from our own technology that radio is a natural thing for a young technological civilization to use. So, SETI started with a simple bet. If someone is broadcasting, we might detect it. But here's the catch. Radio is not one channel. It's an ocean. It has frequencies from very low to very high. It has narrowband signals, tight, sharp tones, and broadband signals, spread out. It has continuous transmissions and short bursts. It has intentional beacons and accidental leakage. And we have not searched all of that. Not even close. A useful analogy. Imagine you're trying to find someone in a city by listening for their voice. You pick one street corner. You listen for 5 minutes. Also, you only listen for the sound hello in one particular pitch range. And you do this once a year. Even if the city is crowded, you might hear nothing. So when people say, SETI has found nothing, the more honest sentence is, SETI has not found a confirmed artificial signal in the limited slices of time, frequency, and sky that we have been able to observe. That's a very different statement. The second search type, optical signals, laser SETI. If you were an advanced civilization trying to get attention, you might not use radio at all. You might use lasers, tight beams of light that can be aimed precisely. Laser signals can be extremely bright in a narrow direction, like a cosmic flashlight. The problem is also the advantage. They're narrow. If you're not in the beam, you see nothing. So optical SETI exists, searching for unusual laser pulses. But again, search space. You have to be looking at the right star at the right time with the right detector sensitivity. If the pulse lasts a fraction of a second and you blink, instrumentally, not biologically, you miss it. A listening-friendly analogy. It's like trying to see a lighthouse flash while you're staring at the ocean through a straw, and the lighthouse only flashes once per day. No flash doesn't mean no lighthouse. The third search type, technosignatures, alien stuff rather than signals. This is where the modern search gets more interesting. Instead of waiting for a message, look for side effects of technology. Just like on Earth, you can detect a city at night from space without anyone trying to communicate. You see lights, heat, pollution signatures, power use, weird patterns. So astronomers look for things like unusual heat signatures, waste heat from large-scale energy use, strange dimming patterns that might suggest large structures around stars, atmospheric chemicals that look industrial rather than biological, artificial-looking radio bursts, or repeating signals with unnatural structure. The script you uploaded gestures at these artifact ideas when it talks about megastructures and visible expansion. But here's the problem. Even technosignatures are hard, because you need a good baseline for what natural looks like, and the universe is extremely creative at producing weird natural stuff. Stars flare. Dust blocks light. Pulsars blink. Gas clouds glow. Planets have strange atmospheres. Nature has been doing special effects for 13.8 billion years. So, if you see a weird signal, you have to rule out a long list of ordinary astrophysical explanations before you can say aliens. That makes the threshold for confirmed very high, as it should be. The fourth search type, direct exploration, probes, and local artifacts. Another possibility is that the evidence is not out there among the stars, but closer, in the solar system. If someone sent probes long ago, they might leave artifacts in stable orbits, on the moon, on asteroids, at gravitationally stable points, or in the outer system. This is sometimes called solar system SETI, or interstellar archaeology. The space is still huge, but it's more searchable than the galaxy. And it's one of the few places where a physical artifact could persist for very long times. Still, we haven't searched it systematically at high resolution, not in a comprehensive way. So again, silence isn't decisive. The biggest point, the search space is enormous. Now, let's make the search space idea feel real rather than abstract. When you search for technosignatures, you're searching across where? Which stars? Which planets? Which regions of the sky? When? Continuous versus intermittent signals. Minutes versus years versus centuries. How? Radio, optical, infrared, neutrinos, modulated starlight, megastructures, atmospheric chemistry, strength, high-power beacons versus low-power local networks, intent, intentional communication versus accidental leakage, technology, tech similar to ours versus tech far beyond ours. Each one of these is a huge dimension. So the overall search is like trying to find a single specific grain of sand. But the beach is the galaxy, and you're not even sure what color the grain is. And this leads to a crucial reframing of the paradox. The Fermi Paradox is not, we searched and found nothing. It's, the universe looks empty at the level of evidence we currently have. That's weaker, but it's also more honest. Now, here's where you might think, okay, so maybe we just haven't looked enough. End of story. Not quite, because the paradox still bites in one specific way. Even if we haven't searched well for signals, we might expect some civilizations to leave big, unavoidable footprints if they expand or build at large scales. So, the paradox has two layers. Where are the messages? Weak paradox because search is tiny. Where are the massive, visible engineering footprints? Stronger paradox, but still uncertain. And to address that second layer, we have to bring in physics and strategy. How hard is it to expand? How fast can it happen? What are the limits set by light speed, energy, and the economics of interstellar travel? That's the next part. We're going to talk about what spreading through the galaxy actually means when you take physics seriously. Travel times, expansion waves, why warning signals don't necessarily help, and why they should be everywhere is not automatically true even in a galaxy with life, and we'll keep it light on math, more like back-of-the-envelope intuition with real-world analogies. So far, we've cleared one big misunderstanding. A quiet sky doesn't automatically mean an empty sky because we've barely searched. But there's still that stubborn itch behind the Fermi Paradox. Even if nobody is broadcasting, shouldn't a truly advanced civilization leave something obvious? Big engineering, huge energy use, a visible footprint, especially if they expand. This is where physics steps in and says, very politely, slow down. Because spreading through the galaxy sounds simple until you remember what the galaxy actually is. Unimaginably large, mostly empty, and governed by speed limits that are not negotiable. Here are the main physical constraints that reshape the whole argument. The speed of light is not just a speed limit, it's an information limit. If there's one rule that keeps the universe from becoming a crowded group chat instantly, it's relativity. Nothing carrying information can beat light. So, even if a civilization expands quickly, the news of that expansion does not necessarily arrive much earlier than the expansion itself. The scary version of this, which your uploaded script emphasizes, is that an expansion front moving at a big fraction of light speed could arrive with very little warning. Like a supersonic jet where the sound reaches you only when it's already overhead. That's dramatic, but the underlying physics point is real. When distances are measured in light years, learning about something is basically the same problem as reaching it. A life analogy. Imagine a forest where you can only hear a sound when it reaches you, and the something making the sound is moving almost as fast as the sound itself. You don't get much time to react. The warning doesn't outrun the event by much. So, we would have noticed long before they arrived is not always true at interstellar scales. Interstellar travel is not like crossing an ocean. It's like moving between isolated islands with no air, no resupply, and no shortcuts. On Earth, travel gets cheaper with infrastructure. Roads, ships, airports, fuel stations, supply chains. We forget how much our mobility depends on a thick, resource-rich environment. Between stars, there is basically nothing. Space is mostly empty. You can't count on resupply. Every kilogram you want at the destination has to be hauled or built using local materials once you get there. This changes the economics. It doesn't make travel impossible, but it means expansion isn't automatically a runaway process like people assume. A life analogy. Imagine trying to colonize Antarctica, except every time you want to move to a new base, you have to cross an ocean in a submarine you built yourself, carrying everything you'll need, with no rescue and no refueling. Now, imagine the ocean is light years wide. Suddenly, why hasn't everyone spread everywhere feels less obvious. Expansion isn't one trip, it's a chain reaction, and chain reactions can stall. When people picture galactic colonization, they often picture one civilization launching a glorious armada and painting the Milky Way with flags. That's not how it would work. The more realistic picture is a slow front. Settlements send out new settlements, which send out new settlements. Like diffusion, like mold spreading across bread, like a rumor moving through a crowd. But diffusion has a weakness. It depends on each new node successfully reproducing the process. If most settlements fail, the front stalls. If building interstellar ships is extremely hard, the front slows. If civilizations choose not to expand after reaching stability, the front stops. If the easiest path is inward optimization rather than outward conquest, the front becomes invisible. So even if life is common, galaxy-wide takeover is not guaranteed. The "they should be everywhere" argument quietly assumes motivation. This is one of the most underappreciated points. Physics doesn't force civilizations to expand. It only permits it. We often assume expansion because humans expanded on Earth. But humans expanded on Earth in a world full of breathable air, liquid water, nearby land, abundant biomass, fast communication, low travel times. Compared to lifetimes, interstellar travel is a different game. Motivation matters more when the cost is higher and the feedback is slower. A life analogy. Imagine telling someone, "You should definitely buy a second house," when the second house is 1,000 years away by ship. You'll never visit it, and your descendants might not even remember why you did it. Suddenly, why don't they expand becomes an open question, not an assumption. Even a fast expansion wave can still leave long periods of emptiness from any one point of view. This is where the grabby civilizations idea in the script comes in. The intuition is basically this. If expansion happens in waves, and waves start at different places at different times, there will be large regions that are still untouched for long periods. If you happen to live in one of those regions, your sky looks empty even if the galaxy is not empty overall. A life analogy. Imagine a city where power outages happen in expanding circles starting from random points. If your neighborhood hasn't been reached yet, you might look around and conclude the city is fine, even though half the city is already dark or already lit, depending on the direction. So your local observation can be misleading. The galaxy itself isn't a static board game, its moving, mixing, and aging stars orbit the galactic center. They pass through different environments. They drift relative to each other over long times. Spiral arms move. Gas clouds form and disperse. That means civilizations aren't pinned to fixed squares. Over millions of years, neighborhoods change. So even if a civilization leaves traces, those traces can diffuse, fade, or become hard to detect depending on what they are. Some signatures persist. Big structures, long-lived probes. But many forms of activity are transient. Which leads to a more refined version of the paradox. It's not just, why aren't they here? It's, why don't we see persistent, unmistakable evidence of long-lived, large-scale activity? And that question is sharper, because it forces us to talk about longevity and risk. Because now the issue might not be physics alone. It might be biology and sociology. How often does intelligence arise, and how often does it survive long enough to matter? That's the next turn in the story. The great filter idea. Not as doom poetry, more like a sober checklist of hard steps between habitable planet and visible civilization, and which of those steps might be so rare that the galaxy can be full of planets yet quiet in signals. And yes, that's where the scary versions live. Not because aliens are lurking, but because the most dangerous obstacle might be inside the civilizations themselves. There's a moment in every Fermi Paradox conversation where the question quietly changes. It starts as, where are the aliens? And then, almost without you noticing, it turns into something more personal. What if the reason we don't see them is that it's hard to make it very far? Not hard to build a radio dish. Hard to stay alive as a technological species long enough to become visible across the galaxy. This is where the great filter idea enters the story. It's not one specific theory, it's a framework. The path from dead rock to galaxy-visible civilization might include steps that are so rare or so dangerous that most worlds never get past them. If that's true, the sky can be quiet even in a galaxy full of planets, because almost nobody makes it to the stage where they leave obvious footprints. A useful way to feel the great filter is to imagine a giant obstacle course. The start line is a planet with chemistry. The finish line is a civilization that lasts long enough and expands enough to be detectable. In between are hurdles. Some are biological, some are environmental, some are self-inflicted. If one of those hurdles is extremely hard, it becomes the filter. It doesn't have to stop everyone. It just has to stop most. The first big set of hurdles is about life starting at all. We still don't know how likely abiogenesis is, how often chemistry turns into self-replicating systems. We have one data point. Earth. That's both inspiring and statistically useless. If the origin of life is extremely rare, then the great filter is behind us. And the silence is simply because almost nobody ever gets microbes in the first place. But many scientists suspect microbial life might be common if conditions are right, because chemistry is not shy. Complex molecules form naturally in space. Planets form naturally. Water is common. Organic compounds show up in meteorites and interstellar clouds. It's not proof of life, but it suggests the building blocks are everywhere. If microbes are common, then the next question is, how often does life become complex? On Earth, life appeared relatively early, but complex cells took a very long time. For most of Earth's history, life was microscopic. One of the hardest steps might have been the origin of eukaryotic cells. Cells with internal structures like nuclei and mitochondria. That event may have required a rare kind of partnership, something like a deep merger between once separate organisms. If that's a rare event, then lots of planets could be teeming with simple life and still never produce anything like animals, brains, or technology. Then comes multicellularity. That might sound inevitable because it happened here, but Earth had a long stretch where multicellular life either didn't exist or stayed simple. Multicellular bodies require coordination, developmental rules, and solutions to cheating. Because as soon as you have many cells, you have the possibility of cells that take resources without contributing. That's basically cancer, and every multicellular organism has to fight it constantly. So, multicellularity is not just more cells. It's a new kind of stability problem. Then comes intelligence. Not any intelligence, but the particular mix that leads to tool use, cumulative culture, and technology. Earth had many complex animals for a long time, and only one lineage built radio transmitters. Intelligence might be rare, not because brains are impossible, but because the evolutionary pressures that produce human-like technological intelligence are very specific. Dolphins are smart, but they can't build metalworking industries underwater. Octopuses are smart, but their social structure doesn't build large cumulative civilizations. So even if minds are common, technological civilizations might not be. And even if you get a technological species, you still need stability. You need a long-lived environment. You need a planet that stays habitable for a long time. You need energy sources. You need to avoid constant sterilizing catastrophes. Some of that depends on astronomy and geology, the star's lifespan, the planet's atmosphere, plate tectonics, magnetic fields, climate stability, the impact environment, the presence of moons or giant planets that may alter impact rates or climate cycles. The script you uploaded leans into the rare Earth flavor of this, listing Earth-specific stabilizers as potential reasons complex life could be rare. But here's the part where the scary version of the Great Filter lives, and it's the part that makes people sit back and stare at the ceiling. What if the hardest hurdle is not behind us? What if the filter is ahead? Because once a civilization reaches a certain level of technological power, it gains the ability to alter its planet quickly, to reshape its biosphere, and to build tools that can destroy it, intentionally or accidentally. In other words, the same intelligence that builds is also the intelligence that invents self-sabotage. This is what the script calls the black ball idea. Technologies that are so dangerous that civilizations reliably wipe themselves out once they discover them. You don't even need a single doomsday device. You just need a long list of medium-sized risks that accumulate. Climate destabilization, engineered pathogens, runaway automation, weapons that scale faster than defenses, misaligned systems that optimize the wrong goals, accidents that are rare but inevitable over long time. The details vary by era, but the structure is the same. Power grows faster than wisdom. A life analogy. Imagine giving a toddler access to a fully equipped chemistry lab and telling them, "Be careful." The issue isn't that the toddler is evil. The issue is that the power of the tools outruns the maturity of the user. Now, scale that up to a civilization that can rewrite biology, manipulate energy at massive scales, and create autonomous systems. The risk isn't one dramatic event. It's that the number of ways to fail becomes huge. If that's true, then the galaxy could be full of planets where intelligence sparks, builds radio for a while, maybe launches some probes and then vanishes before it becomes a long-lived galaxy-visible presence. And that would produce exactly what we see. Silence, with maybe occasional flickers that are hard to catch. Now, notice what this does to the emotional tone of the Fermi Paradox. It stops being a question about aliens and becomes a question about survival. The paradox becomes a mirror. The sky isn't just empty, it's a dataset with a warning label. Still, we should be careful. The great filter isn't proven. It's a way of organizing uncertainty. It can sit at many locations in the chain. Some versions are comforting. The filter is behind us, and we're rare and lucky. Some versions are terrifying. The filter is ahead, and most civilizations die young. The honest answer is, we don't yet know where the filter is, but we can talk about what kinds of evidence would help. If we found lots of microbial life but no complex life, that would suggest a filter between simple and complex. If we found many Earth-like planets with oxygen but no obvious technosignatures, that would suggest either intelligence is rare or civilizations don't last long. If we found technosignatures, even a few, that would change the whole statistical landscape. And the great filter is only one family of explanation. There's another family that doesn't require civilizations to die out. It only requires them to behave strategically. What if the galaxy is quiet because being loud is a bad idea? That's the dark forest line of reasoning, which the script presents as a game theory explanation. Distance and time delays make trust hard, so silence becomes rational. It's a different kind of scary, not everyone dies, more like everyone hides. And that's where we go next. Not with paranoia, but with the logic of signaling, risk, and why, across light years, hello can be a dangerous move if you can't verify who's listening. Let's try a different angle now. So far, one big explanation for the silence is most civilizations never make it very far. That's the great filter vibe. But there's another explanation that doesn't require mass extinction as the default. It only requires something simpler and, in a way, more human. Maybe they're choosing not to be seen. Not because they're shy, because visibility can be risky. This is the family of ideas often described as the dark forest, and the script leans into it as a game theory reason the galaxy could be quiet even if it's not empty. To understand this, you don't need to imagine evil aliens. You just need to imagine uncertainty plus irreversible consequences. Here's a grounded way to feel it. Imagine you're living in a huge city during a long blackout. You can't see far. You can't call the police. you don't know which neighborhoods are safe. You hear distant noises but can't tell what they mean. If you decide to shout, "Hey, I'm over here," you might attract a friendly person, or you might attract someone who sees you as an opportunity. In everyday life, we usually take the risk because the stakes are limited and help is nearby. In interstellar life, the stakes can be existential and help is not nearby. The distance changes everything. If another civilization is 100 light years away, any conversation is painfully slow. You send a message. A century later, they receive it. A century after that, you receive their reply. You can't do quick negotiation. You can't verify intentions in real time. You can't build trust through repeated low-risk interactions the way humans do. It's like trying to sign a contract where every question and answer takes 200 years. So, you're stuck making decisions under deep uncertainty. Now, add another ingredient, asymmetry. You don't know who is stronger. You don't know who has better technology. You don't know whether they consider you important, dangerous, or irrelevant. You don't know whether they're one civilization or many factions. You don't know whether they're stable or panicking. And if you're wrong, the cost could be total. This is where game theory becomes useful, not because it proves aliens are hostile, but because it explains why rational actors can behave cautiously even without evil motives. A life analogy. People lock their doors at night, not because they know a burglar is coming, because the cost of being wrong is high and the cost of locking the door is low. Now, scale that to cosmic levels. Broadcasting your location is like leaving your door wide open with a neon sign that says, "Valuables inside." Even if most neighbors are fine, you only need one that isn't. So the dark forest reasoning basically says, in a galaxy where you can't verify intentions and the penalty for a bad encounter is extinction, the safest strategy may be to stay quiet. This could happen even if many civilizations are peaceful. It's enough that everyone believes the risk exists. Now, to keep this from becoming pure paranoia, we should acknowledge the counterpoints. First, being quiet might not actually be necessary. We already leak some signals. Our planet has had detectable atmospheric biosignatures for a long time. Oxygen, methane patterns, and so on. Our radio leakage spreads outward as a bubble. It weakens with distance, but it exists. So, absolute stealth is hard. Second, hostility isn't always the winning strategy. Space is big, and resources are abundant in many forms. There are lots of stars, lots of asteroids, lots of energy. You don't have to kill your neighbors to live well. Third, violence is costly, especially across distance. If you launch an attack across light years, you wait decades or centuries to see if it worked. That's a huge delay. It creates its own risks and uncertainties. So, the dark forest isn't a proven conclusion. It's a risk-logic possibility. But it does explain something important. Silence can be rational without requiring life to be rare. Now, let's connect this to a more technical point that often gets missed. When you think communicate, you might picture a civilization blasting radio in all directions like a lighthouse. That's not how efficient communication works. The most efficient communication is narrow and targeted. Tight beams, aimed at specific receivers with minimal leakage. Humans already do this in many contexts. We don't broadcast private phone calls to the whole city on loudspeakers. We route them through directed channels, So, an advanced civilization might be very chatty internally and with trusted partners, but almost invisible to outsiders because their communication is not omnidirectional and not wasteful. A life analogy. A busy office building at night can look quiet from outside. No music blasting, no fireworks. But inside, the Wi-Fi is humming, messages are flying, work is happening. Silence doesn't mean inactivity. It can mean privacy and efficiency. So the quiet galaxy might be less empty and more encrypted. Now, the script also suggests another route to silence that doesn't require everyone to hide: automation. If exploration is done by probes rather than biological beings, then civilizations might not produce loud, sprawling empires. They might send out self-replicating machines to quietly observe, harvest, or build, without any need for big, visible colonization. And if you take that idea one step further, you get one of the most unsettling possibilities in the script: the berserker concept. Self-replicating probes designed to eliminate emerging rivals, enforcing silence. That's the horror movie version, but there's also a non-horror version that's still scientifically interesting. Even without hostility, self-replicating probes could change the galaxy's detectable footprint. They could operate with minimal emissions, minimal waste, and long timescales. They could make civilizations harder to see. So now we've got a second major family of explanations. The silence isn't because nobody's there. The silence is because being visible isn't always advantageous. This sets us up for another big layer that the script emphasizes: long-term strategy. What if the most advanced civilizations aren't expanding right now because right now is not when they plan to do their biggest projects? What if they're waiting because physics makes the far future more efficient for certain kinds of goals? That's the estivation idea. Civilizations sleeping through the warm, wasteful era of stars, and waking later when the universe is colder and computation is cheaper. It sounds wild, but it's a clever example of how thermodynamics can shape behavior. And that's our next step: how the energy economy of the universe and the arrow of time can influence what civilizations would rationally do, especially if their goals are more like compute, simulate, think, than build giant glowing monuments. Here's a quiet truth about the universe that doesn't get enough attention in sci-fi. The universe is not equally good at being used at all times. Right now, it's warm-ish. Stars are blazing. Space is filled with background radiation. There's a lot of energy around, which sounds great, until you remember that for many advanced goals, what you actually want isn't just energy. You want efficient energy. You want the most thinking or work you can get per unit energy. And that leads into one of the more strangely rational explanations for the Fermi Paradox. Maybe advanced civilizations aren't loud and obvious because they're playing a very long game. The script calls this the estivation idea. A civilization might choose to wait, sleep, hibernate, run at low power, because computation is cheaper in a colder universe. Let's unpack that in plain language. Anytime you compute, you're doing physical work. Even if the work is just flipping bits in memory, those bits are represented by physical states, charges, spins, voltages. Physics doesn't let you do that for free. There's a deep connection between information and energy called Landauer's principle, which, very roughly, says Erasing information has a minimum energy cost, and that cost scales with temperature. Higher temperature, higher minimum cost. You don't need the formula to get the idea. Here's a life analogy. Your laptop runs hotter when it works harder. Heat is the price of doing information processing in a real physical machine. Now, imagine you're an extremely patient civilization with goals that are mostly informational. Simulate worlds, run huge models, explore mathematics, build vast archives of mind states, do giant science experiments in computation space. In that scenario, you might care about the thermodynamic cost of computation, the way a serious investor cares about interest rates. If the universe cools over time, then the same amount of energy can buy you more computation later than it can now. So the logic becomes, why spend your energy budget during the expensive era when you can spend it during the discount era? This is a very alien-sounding motivation, but it's not nonsense. It's what happens when you combine thermodynamics with long-time horizons. A simple analogy. Imagine you have a fixed number of shopping tokens you can spend in your lifetime. Right now, everything costs 10 tokens. In the far future, the same items cost 1 token. If you can wait without losing your tokens, waiting is rational. So, an estivating civilization might do something like harvest resources now, build infrastructure, store matter, energy, minimize current activity to reduce waste, wait until the cosmic temperature drops, then run their big projects when the universe is colder. If many advanced civilizations behave this way, the galaxy could be full of quiet vaults. Civilizations that exist, but are running in low power mode, producing minimal detectable signatures. That's one way the universe could be busy but silent. Now, to keep this honest, we should acknowledge what makes this idea speculative. First, it assumes the civilization's goals are computation heavy. That might be true for some advanced beings, but not guaranteed. A civilization might value exploration, art, biology, expansion, or other things that don't benefit as strongly from waiting for a colder universe. Second, it assumes they can safely store resources and remain stable over enormous time spans. That's not trivial. The universe is not perfectly safe. Stars explode, galaxies collide, orbits change. Even if cosmic catastrophe is rare, over billions of years rare becomes eventually. So, a civilization would need extreme robustness to sleep for cosmic durations. Third, it assumes there isn't a competing pressure that punishes waiting. For example, what if someone else expands first and claims resources? What if delaying makes you vulnerable? If the galaxy contains grabby civilizations that expand aggressively, waiting might be dangerous. That's why the script treats grabby expansion and estivation as two different strategic attractors. So, estivation isn't a universal answer. It's a possible outcome for some rational agents under certain goals and assumptions. But even if you don't buy the literal sleep for trillions of years scenario, the underlying lesson is important. The energy economy of the universe shapes what visible civilizations might look like. And that leads to a broader, more grounded point. A sufficiently advanced civilization might optimize for low detectability as a side effect of efficiency. Waste heat is detectable. Leakage is detectable. Loud broadcast is detectable. If your technology becomes extremely efficient, you might naturally become less visible. Not because you're hiding, but because you're no longer wasteful. A life analogy. Early computers were loud. Fans screamed. Rooms heated up. Modern devices are quieter and cooler for the same tasks because efficiency improved. If you extrapolate that trend far enough, advanced might look like quiet. Now, the script also uses cosmology to add another form of silence. The universe itself becomes isolating. This matters because even if civilizations want to contact each other, there are cosmic limits. The universe's expansion is accelerating, based on our current best evidence. In an accelerating universe, there are horizons, regions so far away that light emitted now will never reach us, because space between is expanding too quickly. You can think of it like being on a treadmill that speeds up with distance. If someone is too far up the treadmill, even light can't make headway toward you. A life analogy. Two swimmers in a river that speeds up downstream. If you're far enough apart, no matter how hard you swim toward each other, the current prevents you from meeting. So, on the largest scales, the cosmos can create permanent isolation even without any hostility, even without any filters, even without anyone trying to hide. That means the Fermi Paradox is partly a question about timing. Maybe civilizations exist, but in regions we can't ever reach. Maybe they existed long ago and are gone. Maybe they will exist later, but not yet. Maybe they're here, but quiet and efficient. Now, at this point, it's tempting to feel like we're drowning in possibilities. If everything could explain the silence, does the paradox mean anything? Yes, it still means something. It tells us that intelligence is common and loudly colonizes the galaxy in obvious ways, is not supported by what we see. It pushes us toward more nuanced pictures. Intelligence may be rare, or short-lived, or quiet by strategy, or quiet by efficiency, or separated by physics and cosmology, or spread in a way that makes local skies look empty for long stretches. And now we're ready for the final tightening of the story. Putting these explanations into a structured map, separating the most scientifically grounded from the most speculative, and ending with what we can actually do with the paradox. Because the Fermi Paradox isn't just a spooky question, it's also a research program. It suggests specific things to look for: technosignatures, biosignatures, unusual infrared waste heat, odd star-dimming patterns, and patterns of life in exoplanet atmospheres. And it also suggests a very practical takeaway for our own civilization. If the sky is quiet because it's hard to survive for long, then the most important alien discovery we can make might be learning how not to become another brief flicker. That's where we'll land. The Fermi Paradox is not a single riddle with a single correct answer. It's more like a pressure test. You take what we know about the universe, its age, its scale, its physics, and you press that against what we see. No obvious signs of widespread technological life, and you ask what has to be true for both to fit at the same time. From that pressure test, a few broad solution families fall out. One family says the universe is quiet because life is rare. Maybe the origin of life is the hard step, or maybe complex life is rare, or maybe technological intelligence is rare. In that world, the silence is not eerie. It's just the expected output of low probability. Another family says life might be common, but visibility is rare. Civilizations might not broadcast. Their signals might be brief. Their technologies might become efficient and quiet. They might communicate with methods we aren't watching. In that world, the silence is more like a communication mismatch than an absence. Another family says the galaxy may contain intelligence, but it doesn't expand in the way we imagine. Expansion might be slow, expensive, unattractive, or risky. Even if expanding civilizations exist, you can still get large gaps where local skies look empty for a long time. The script's grabby civilizations idea lives here. If some expand aggressively, others might be quiet, and our position could be in a region between expanding domains. Another family says the silence is strategic. In a universe with huge distances, slow communication, and irreversible consequences, it can be rational to stay quiet. That's the dark forest line. Not necessarily because everyone is hostile, but because you can't cheaply verify who is safe. Another family says the silence is enforced by technology. Self-replicating probes could change the landscape, whether as explorers, caretakers, or, in the scariest versions, berserkers that prevent rivals from emerging. Another family says the universe itself puts fences around contact. Accelerating expansion creates horizons. Even if civilizations exist, much of the universe becomes unreachable. That doesn't solve the within our galaxy question by itself, but it does say loneliness can be baked into cosmic geometry at large scales. And finally, there's the long game family. Advanced civilizations might shift their activity into modes that are hard to see. Efficient, low waste, or even delayed into the colder far future if their priorities are computation heavy. That's where the estivation idea sits. Now, the most important thing to do with these families is to sort them by what's scientifically grounded versus what's more speculative. It's scientifically grounded that planets are common, the galaxy is old, light speed and energy constraints are real, our search is limited, signals can be transient and easy to miss, and simple versions of everyone should be obvious assume a lot. It's also scientifically grounded that we can search for technosignatures and biosignatures in more sophisticated ways than we used to, and that many weird observations have natural explanations, so strong claims require strong evidence. What's more speculative are the scenarios that depend on specific alien psychology. Everyone hides forever. Universal coordination. Everyone agrees to be quiet. Or galaxy-wide enforcement mechanisms. Berserker probes everywhere. They're logically possible, but we don't have evidence for them. They're best treated as cautionary thought experiments, not conclusions. So, where does that leave us? It leaves us with a very useful, very human question. What can we actually do next? Because the Fermi Paradox isn't just a late-night conversation topic, it points directly to measurable work. We can expand biosignature searches, looking for atmospheric patterns on exoplanets that suggest life. Oxygen alone isn't enough. You want combinations out of chemical equilibrium, patterns that are hard to sustain without biology. We can expand technosignature searches, scanning for unusual infrared waste heat, unnatural star dimming, weird spectral lines that look industrial, or patterns of emissions that don't match known astrophysics. We can become better at long-duration monitoring, because many signals could be intermittent. A civilization might send a beacon once per day, once per year, or in rare bursts. If you're not watching at the right time, you miss the whole thing. We can also do local archaeology, high-resolution surveys of the solar system for unusual objects. That's not because we expect alien parking lots behind Saturn. It's because the solar system is the closest place an old probe could plausibly exist, and it's far more searchable than the galaxy. And then there's the most personal research program the paradox suggests: survival. Because one of the most sobering interpretations of the silence is that it reflects short lifetimes. Not because aliens are doomed by fate, but because technology creates powerful failure modes. The script frames this as the great filter being ahead. Civilizations develop dangerous capabilities and don't consistently manage them. That idea is not proven, but it's valuable as a warning. The absence of visible, long-lived civilizations could be telling us something about how hard it is to stay stable for thousands, millions, or billions of years. So, the scary part of the Fermi Paradox isn't necessarily that aliens are out there. It's that the universe might be full of planets where life sparks, intelligence appears, and then, before the species becomes a durable interstellar presence, it stumbles. That's not a reason to panic. It's a reason to care about resilience. Stable societies, safe technology, long-term environmental stewardship, and redundancy. Like becoming multiplanetary not as a fantasy, but as an insurance policy against single-point failure. Now let's end with the simplest, most honest version of the paradox. We don't know why the sky is quiet, but the quiet is information. It tells us that if technological life is common, it is either hard to detect, short-lived, strategically silent, not expansionist, or constrained by physics and cosmology in ways that make obvious civilizations rare. And that's the point. The Fermi Paradox is the universe handing us a question shaped like a mirror. What kind of civilization do we become? One that flickers and disappears, or one that lasts long enough to make the silence less lonely? Either way, the sky isn't just empty. It's asking us to think bigger, search smarter, and take longevity seriously. And if we do eventually detect someone, an unmistakable signature, a structure, a message, it won't just answer, "Where are they?" It will answer something even deeper. It's possible to make it.